Okay, so in this video, I'm going to be going over section 5.5, which is about rational functions and the properties of rational functions. So we're going to be talking about how to graph rational functions and how to identify their vertical and horizontal asymptotes or oblique asymptotes. So, as we know, a rational function is a function that has the form of a p of x divided by q of x, which means this is a polynomial function of x and this is a polynomial function of x. So we know that a rational function means we have a variable in the denominator. So both the numerator and the denominator can both be a function of x. And that denominator q cannot be 0. Obviously, we cannot divide by 0. That will give an undefined result for this function. And the domain of a rational function is the set of all real numbers except any values of x that makes the denominator equal to 0. So we should be familiar with this by now, how to find the domain of a rational function. But we're going to go over a couple of quick examples just to remind ourselves. So the first one is the function 3x squared minus 5 over x plus 2. So when we're asked to find the domain of this function, it can be any number except for any values of x that makes that denominator equal to 0, since we can't divide by 0. So therefore, x cannot equal -2. But it can equal any other number. So this is the domain of this function r of x in set notation. The second example is the function of r of x is equal to 1 divided by x squared minus 25. I can find the domain of this by first figuring out which values of x makes the denominator equal to 0. So that x squared minus 25 is a difference of two perfect squares, so that factors to x minus 5 times x plus 5. And so therefore there are two values that x cannot equal, and that will be positive 5 and negative 5. But it can equal any other number. So the domain is all numbers except for negative 5 and 5. Last one is the function 2x cubed over x squared plus 1. If I tried to set that denominator equal to 0 to solve, to see which values gives me 0 for that denominator, you'll find that you will get an imaginary number because I subtract 1 to both sides and I'm left with x squared is equal to -1. So if I take the square root of both sides, then I get x is equal to plus or minus I, imaginary I. And so this is not a real number that will make the denominator equal 0, so therefore the domain is all real numbers. In interval notation, this would be from -infinity to infinity. Because there is no real number that will make the denominator equal to 0. Okay. I thought the last one was the last one, but this, I believe, is the last one, yeah. Okay, so this one is the function x squared minus 4 divided by x minus 2. So we see that the domain is the set of all real numbers except for 2. So x cannot equal positive 2 or it'll make that denominator equal to 0, which we cannot have. Now if we notice something, and I'm going to write it up here. If I factor the top is a difference of two perfect squares. So that'll factor to x plus 2 times x minus 2. And it's all over x minus 2. So if you notice up here, these x minus 2's will cancel. So this is actually equal to x plus 2, r of x. But because it started out as a rational function, the rational function x squared minus 4 divided by x minus 2, and that linear equation, x plus 2, which it simplifies to, these are not the same functions since it started out as a rational function to begin with, because of that domain difference. See, this is just a regular line, so the domain of x plus 2 would be all real numbers. But if I'm asked to find the domain of this rational function, x cannot equal 2. So therefore, there will be a hole in the graph at x is equal to 2. It'll actually look exactly like this line of x plus 2, but there will just be a hole in the graph where x is equal to 2. Because if I plug 2 in that function, it'll be undefined. But the rest of these values on this table are comparing y1 is the rational function, and y2 is equal to that x plus 2. So they have all the same exact output values for each x value except for when x is equal to 2. All right, so let's analyze a few of these functions, rational functions. So the first one is the function h of x is equal to 1 over x squared. So to analyze the graph of this function, first we're going to find the domain. So the domain is all real numbers. So the set of all x such that x cannot equal 0, because if I plug 0 into that denominator, then I'll get 0 in the denominator. Okay, now the y-intercept, remember we find by plugging 0 in for x? Well, I can't plug 0 in for x. Because it's not in my domain. So therefore, there are no y-intercepts. To find the x-intercepts, I set the entire function equal to 0. So 1 over x squared is equal to 0. To try and solve this, I would have to multiply both sides by x squared to cancel my fractions. But this will give me 1 is equal to 0, which is false. So therefore, there's no solution. So no x-intercepts. And then let's determine whether it's even, odd, or neither. So I will plug in negative x into my function, and this will give me 1 over negative x all squared, which is the same thing as 1 over x squared. So therefore, since we plugged negative x and got back the original, this function is even, so it is symmetric about the y-axis. So let's look at the graph and compare with everything that we just found. No y-intercepts, no x-intercepts, and the function is symmetric about the y-axis. So here is the graph of 1 over x squared. So we see in the picture that this graph will never cross the y-axis, and it's getting really, really close to the x-axis, but it's never going to cross the x-axis either. We just found that there are no x or y-intercepts. But what happens when, what happens to the graph as the values of x get closer and closer to 0? So if I'm trying to figure out what's happening to the graph as x is getting closer to 0, well, here's x is 0. So if I'm looking from the left, I'm looking as x gets closer to 0, it starts shooting up to positive infinity. And if I look from the right, as these values get closer to x is 0, it also shoots up to positive infinity. But let's look at the table. So if you go into your graphing calculator and you type in this function, y equals 1 over x squared, into the y equals button, and then you click on, I'll show you. So I have that function already in the y equals 1 over x squared. If I go to second table set, and well, really the rest of this doesn't really matter, but if I change the independent to ask, so if it was on auto, I'm going to switch it to ask and click enter. That way, so all you have to do is hit enter and change independent to ask, and then I'm going to click second graph to go to my table. Okay, so if I clear these, let me see. Sorry. Second, quit. Okay, second table. All right, it's not gonna, can I delete? Yeah, okay. Okay, so when you first go, it should look like this. Now you can pick any value for x that you want to analyze for y1. So if I put 0, I get error, because we just seen that 0 is not in the domain of 1 over x squared. If I put 0.01, it's really big. If I put 0.001, it gets bigger. 0.0001, it's getting bigger. So as x is approaching 0, 0.00001, my y values are getting really large. And let's go back so I can show you. And just remember, so when we put 1, oops, no, I don't want to do that. When I go to 0.001, my output here is 1e to the 6th. Remember, that means 1 times 10 to the 6th power, which is 1,000,000. So 1 million. So it's getting very large very quickly. Okay. So right now that's just talking about as x gets closer to 0. And so as these values of x approach 0, the values of the function, the output values, become larger and larger positive numbers. So they're getting really, really big. When this happens, we say that our function h of x is unbounded in the positive direction. But usually we really denote this using this symbol here, h of x, right arrow to infinity. And what this says is that our function h of x approaches infinity. So as x is getting closer to 0, our function is approaching infinity. In calculus, we can use the limit notation. So the way that we read this right here is the limit notation that says the same thing as, well, minus the part about x going to 0. But the way we read this is that we say the limit as x approaches 0, as x gets close to 0, then the limit of our function h of x is equal to infinity. So as x gets close to 0, our function gets close to infinity. And so putting all that together, we usually write this notation like this. Our function h of x is approaching infinity as x is approaching 0. Okay. Now we're going to talk about what's happening in our graph as x is approaching infinity. So let me erase this real quick. So when I'm talking about as x approaches infinity, I'm talking about, well, now I'm looking going in the left direction to see what's happening when x is approaching negative infinity, what's my output values, and if I go to the right, I'm looking at what's happening to x as x is approaching positive infinity, when my values of x get really large. And in that graph, it looks like that it's just stopping at y equals 0 here. It'll never cross that, which we've already showed because it doesn't have an x-intercept. Okay, but let's talk about it. So as x is approaching infinity, now we're looking at these values. So I'm putting in values of x as getting larger. So 10, 100,000, and then 10,000. And we look at the output. So at x is 10, I got 0.01 as an output. When x is 100, I get 1 times e to the negative fourth, which is, we show that right here, 1e to the negative 4 means 1 times 10 to the negative 4. And that's that scientific notation, and that means 0.0001. So that's getting closer to 0. And then we keep going as x gets larger, our output values are getting closer to 0. And so in notation wise, we say that as x is approaching infinity, or as x is getting larger, the values of the output h of x are approaching 0. And so this is the end behavior of the graph, because in behavior, I'm talking about what's happening at the end values of x, what's happening at negative infinity and what's happening at positive infinity. And as we've seen, they're getting really, really close to 0, but never touching it. So the end behavior is just describing what's happening at these endpoints as x is getting closer to infinity. And then we can express this notation-wise as the limit of our function h of x as x approaches infinity is equal to 0. And here is a picture of that graph drawn by hand. So they're just kind of plugging some values in to find some points here. Now again, remember we said it would be symmetric about the y-axis, so these points will have symmetry. And then the red dashed lines that you see up here, here, and here, this is kind of representing the ideas that we discussed previously. So as x is approaching negative infinity, my y values are approaching 0. As x is approaching positive infinity, my y values are approaching 0. And as x is approaching 0, getting closer to 0 here, my y values are approaching infinity. On both sides. Okay, so now let's use our transformation knowledge that we learned about to graph this next function using that function we just analyzed, 1 over x squared. So this graph, or this function, is r of x is equal to 1 divided by x plus 1 all squared minus 2. And so we can use this base graph here, 1 over x squared, and graph this using transformations. So we see that the domain is still going, the domain of r of x will change to all real numbers except for x being equal to negative 1, since that will make this equal to 0. So x cannot equal negative 1. And we go to the next slide, and this will show how to graph this using transformations. So we are starting with the graph of h of x, 1 over x squared, which we have already analyzed. And if I do this by pieces, I can graph the first transformation, which is that 1 being subtracted directly from the x. And so this is a horizontal shift in the left direction of 1 unit. And so we see in this graph here that everything has been shifted to the left 1 unit. So what does this do to our vertical asymptote? Before it was x is equal to 0. So since everything is being shifted to the left 1, now our vertical asymptote will become x is equal to negative 1, since that will also shift to the left 1 unit. Everything else about the shape of our graph stays the same, and then we can also move these points over by 1 unit. This point was -1, 1. This point will become -2, 1, and so forth. And then the other transformation that we need to account for is the -2 being subtracted to the entire function. So we just start with this second graph, and now this is a vertical shift going down 2 units. So this will shift our graph down 2 units. Our vertical asymptote will stay the same, but now our horizontal, that line that we said x will never, or sorry, y will never approach. We don't have any x-intercepts. Well, now we will, because I'm moving this entire graph down 2 units. So this, before we had a, let me get a different color. We had like this invisible line here where our graph would never cross. So that invisible line will still follow when I move that down 2 units. So that was at y is equal to 0, and now that will be at y is equal to -2. So our graph will never cross that line, y equals -2. It'll just get really close to -2. So all the same characteristics of the first graph we'll have, but since we're shifting and moving, those vertical asymptotes will move around too. Okay, so let's actually define vertical and horizontal asymptotes. So if we let R denote a function, if as x approaches -infinity or +infinity, the values of this function approach some fixed number L, then the line y equals L will be a horizontal asymptote of the graph of R. So let me just compare that to this function here. So remember, we said that as x was approaching, let me go to this slide actually. As x was approaching -infinity and +infinity, our values were getting very, very, very close to 0. So this is an example of a horizontal asymptote. That function in that example, the y value was getting really close to 0. So that y equals 0 was a horizontal asymptote. And then for a vertical asymptote, if x approaches some number c, and the absolute value of the function goes to +infinity, so that means that either the function's going to -infinity or the function's going to +infinity, then the line x equals c is a vertical asymptote of the graph of R. Okay. So here are a couple examples of horizontal and vertical asymptotes. So the first one is this function r of x. It looks like this little curve. And this function appears to be approaching this line here, y equals L. And it'll never cross that line. So as x is approaching infinity, the values of r of x approach that value of L. So the points are getting really close to that line, y equals L. The next one is also a horizontal asymptote. So this looks like as x is approaching -infinity, the y values are approaching that line, y equals L. So this is another example of a horizontal asymptote. Now we will see that horizontal asymptotes don't always mean that they'll never cross it. We could have a horizontal asymptote that our function will cross. But these are just examples of ones that they will never cross. The next one is a vertical asymptote. use a different color here. And we see here that this function in blue will never cross that vertical line, x equals c. It's approaching it, but it'll never touch it. And the y values of those, that function is shooting up to positive infinity as x approaches that value of c. So this is a example of a vertical asymptote. And then the last one. So this is an example of a vertical asymptote where one side, let's look at the left side here. Left side, as x is approaching that value of x equals c, this function, or the left side, is approaching negative infinity. But if I look from the right, as it approaches c, this function is approaching positive infinity. It's going up. So sometimes the vertical asymptotes can cause your function to go towards positive infinity and negative infinity on either side. And sometimes they can both go to positive infinity on both sides of the vertical asymptote. Okay, so a horizontal asymptote, when it occurs, describes the end behavior as we've seen. I'm going to just say that one more time. Here is our horizontal asymptotes, and when we talk about end behavior, we're talking about what's the y value as x goes to infinity or negative infinity. And so it describes the end behavior as x goes to negative infinity and positive infinity. And like I said, the graph of a function may intersect a horizontal asymptote. So it won't always just never touch it. It could cross over a horizontal asymptote. A vertical asymptote, when it occurs, describes the behavior of the graph when x is close to some number c. So not the end behavior, just the behavior when x gets close or approaches some value c. And for vertical asymptotes, your graph will never intersect. May intersect, never intersect for a vertical asymptote. Now there is a third possibility for a type of asymptote, and it's called an oblique asymptote. And this oblique asymptote is whenever x is approaching negative infinity or positive infinity, and the value of the rational function approaches a linear expression. So it'll actually have the end behavior will mimic that of a linear expression. So there could be some like curves, turning points in the middle, but towards the end, they're just kind of flattening out and looking like some linear function. And the graph of a function may intersect an oblique asymptote. So they can intersect an oblique or a horizontal, but never a vertical. One second. Okay, so locating vertical asymptotes is actually pretty very simple. So the graph of a rational function, p of x over q of x, in lowest terms, so that means after it's been factored, has a vertical asymptote, x equals r, if r is a real zero of the denominator q, which means it makes the denominator equal to 0. So that is if x minus r is a factor of the denominator q of the function r when it's in lowest terms after it's been factored and simplified, then the graph of r has a vertical asymptote at x equals r. So therefore, to find vertical asymptotes, we set the denominator equal to 0 and solve for x after it has been simplified. Have to do that first. So let's see a couple examples. So for A here, and let's just think about this too, okay? Vertical asymptote is what the values that makes the denominator equal to 0. Well, that makes sense because vertical asymptotes are values our function can never touch. So any x value that makes the function undefined, of course, our graph will not be touching because we can't plug it in. It's not in our domain. So at these values of x that makes the denominator equal to 0, that's when our graph does weird things. It's undefined. So that is what creates our vertical asymptotes. It will never touch it because we can't plug that value of x into the function. So here for part A, the value of x that will make f of x undefined would be 3. So the vertical asymptote, which I'm going to shorthand as VA, is equal to the equation x is equal to 3. So whenever you're finding the answers to, when you're finding the vertical asymptote, it'll always be a vertical equation, x equals that number. Okay, B. Here my denominator is x squared minus 49. So if I wanted to figure out what values of x makes that equal to 0, I could set that denominator equal to 0 and solve. So I can add 49 to both sides or factor it, whichever way you want to do it. And so x will equal plus or minus 7. So I have two vertical asymptotes in this case. X is equal to 7 and x is equal to negative 7. That will give me two vertical asymptotes because my graph will never be able to touch at the x value of 7 or negative 7. For C, the denominator is x squared plus 9. If I tried to set that equal to 0 and solve, I would subtract 9, and I see that this is going to give me the square root of 9 times I. So this is imaginary solution. So therefore, there is no real number that will make the denominator equal to 0. So therefore, h of x has no vertical asymptote. The next one is x squared minus 25 over x squared plus 2x minus 35. So this one I'm going to want to factor the top and the bottom. So the top will factor to x plus 5 times x minus 5. The bottom will factor to minus 5 plus 7. And so we see that these x minus 5s will cancel. And this will leave me with x plus 5 over x plus 7. And therefore, our vertical asymptote will be what will make this equal to 0, which would be negative 7. So x is equal to negative 7. Give me 1 second. Make sure. X squared is negative 7 and not 5. Perfect. Okay. So you have to be careful because if these cross out here, then that x minus 5, so 5 will not be a vertical asymptote, only -7 will. So you always need to make sure you factor and simplify first. That rule says it has to be in lowest terms. So the only vertical asymptote will be x is equal to -7. And we're going to talk more about what happens with that x minus 5s when they cancel, but that will create holes in our graph. Okay, so finding the vertical asymptote, not too bad. You just set the denominator equal to 0 and solve. And that's how you find vertical asymptotes. So we've learned about the multiplicity of factors. So if the multiplicity of a real zero that gives rise to a vertical asymptote is odd, then the graph will approach infinity on one side of the vertical asymptote and approach negative infinity on the other side. So this, for example of this one, we had that if I had the equation, the function 1 over x cannot equal 0 here. So that will cause a vertical asymptote at x equals 0, and the exponent on x is 1, so it's odd. So therefore, our graph will look like this. So on the left side, my graph will be approaching negative infinity. And on the right side, the graph will be approaching positive infinity as it gets close to 0. So as it gets close to the middle. It's shooting up on the right and it's shooting down on the left. So that's what that means. But if the multiplicity of the real zero that gives rise to the vertical asymptote is even, then it'll approach either infinity or negative infinity on both sides. So we've seen that with the function 1 over x squared. This multiplicity is 2 on that 0 in the denominator. We said x cannot equal 0. That's our vertical asymptote. And that graph looked like this, where it both headed to positive infinity whenever x was getting close to 0.